purpose of this prerequisite review is to get everybody's head back in the game regarding the quantum theory of angular momentum. Now, we're not going to go into a complete analysis of the entire theory. That's prerequisite material, right? I want to focus these lectures when I do detailed work on things that are very, very essential to understanding QED as a subject. Now, angular momentum, of course, is essential, yes, but the presumption here is that you know quantum mechanics, right? We're just going to focus on those elements of quantum mechanics that we need a little bit more detail and rigorous review of. The quantum theory of angular momentum is just such a fundamental part of it that I feel like the purpose of this is we're going to mind map the entire concept, the entire theory, as far as I can see in all directions. And where you feel weak as a viewer of this material, you go back and review, right? And I should give you more than enough to give you hints about where to go back to. For example, eventually we'll talk about some of the differential operators and equations, and you'll say, hey, gee, that sounds awfully familiar. I remember all that stuff. Or, whoa, I don't think I ever did that fully. Maybe I should go back and do it again. All right? So let's begin. The starting place for almost all undergraduates when they be introduced to the quantum theory of angular momentum is usually the classical theory of angular momentum, right? We start with what is our classical understanding of angular momentum. And the angular momentum is R cross P. P is momentum, R is position. And this starting point is where quantum mechanics often begins. We go to the classical theory, and then we start replacing everything with quantum mechanical operators, right? So in this case, what we would do is we would go to the quantum mechanical operator for momentum, and we say, okay, I'm going to take every place in the classical theory where I see momentum, and I'm going to place this differential operator d by dx. Likewise, I'm going to go to everywhere where I see position vectors, and I'm going to replace it with just the position. This is the quantum mechanical operator associated with position, right? Each coordinate is nicely separated and commutes quantum mechanically. Likewise, each coordinate here commutes quantum mechanically. So what I'm going to now do is I'm going to take those two things and I'm going to go through a process that is often called canonical quantization, meaning I take the classical theory, inject the quantum mechanical operations. Now, we do have to be a little careful when we do this. For example, there's two ways to engage these quantum mechanical operators. One is we can just leave it in this operator form and forget about this, right? Forget about the actual differential operator. Or we can, skip the abstract form altogether and go right to the differential operator. The difference is quite profound, actually, because if we use the differential operator, we're immediately talking now about wave functions, because wave functions are functions of space-time, right? When we write down a wave function, we are saying psi is a function of r, theta, and phi in spherical coordinates, or psi is a function of x, y, and z in Cartesian coordinates. Or likewise, we could use cylindrical coordinates. Usually in quantum mechanics, we're dealing with all flat space-time, and the coordinate systems are usually set up to be one of these sort of standard coordinate systems. There are other coordinates. There's parabolic coordinates and other weird things, and there are circumstances where that all matters. But spherical coordinates and Cartesian coordinates, that's really where we're going to focus our quantum theory out. So once we start, if we choose to use these differential operator replacements in the classical theory, we know right away we're talking about a wave function formalism, right? We talked about the Dirac formalism for about 8 lectures, and this would not be that. This would be the wave function formalism. Otherwise, these differential operators aren't very useful, right? They're meant to take derivatives of functions, and those functions are wave functions. So let's imagine that we actually make that choice, right? We choose to make the canonical substitution of the actual operators themselves, meaning the function z, or the functions of space, the coordinate values multiplying by the coordinate values, and the differential operators. Why does this keep switching to erase mode? So once we do that and we make that insertion, what does that look like? Well, it looks like this, right? We start with L cross P. So we now inject our operators. We get these guys. Right now I've left it as the abstract operators for now, but we're going to replace these with the differential operators, and we're going to replace these with the actual position operators. And so if I were to do that, then I guess this line here would become x partial y minus y partial x, right? And then I would need to make sure I get the units correct. I think it's minus I h bar, right? So this substitution now is the substitution we're talking about. But just for brevity of notation, I'll leave it in this abstract form. But ultimately, we can then create the angular momentum operator as sort of this vector sum of these individual components. Remember, this is the z component of this cross product. This is the y component of this cross product, right? If you remember how to do your standard vector cross products. And then we ultimately get this guy, right? The cross product of the position with IH bar times the gradient operator. And then L squared can be considered as the dot product of L with itself, and you get these expressions here. So let me clean this up a little bit. So that is the process you go through, and ultimately you end up being able to now create these guys, right? In the nice Cartesian system that I just did, you can create these differential operators. And then once you've got the differential operators written down in Cartesian coordinates, it's not much of a thing to then convert to spherical coordinates. And now you have the same differential operators written in spherical coordinates. So the difference is the Lx, Ly, and Lz, you're going to see all three of the variables appear in these expressions. You got y, z, and x. But in spherical coordinates, a nice thing happens where the r value, right? This would normally be r. The three coordinates would be radial coordinate, latitudinal coordinate, and azimuthal coordinate. And the radial coordinate seems to go away, right? So now everything is written in terms of two of these, except for Lz, which is actually only written in terms of one. So this is all very nice. And it turns out that this is the natural coordinate system to understand spherically symmetric problems, which is almost exclusively the problems you solve in elementary quantum mechanics. In elementary quantum mechanics, you're either studying Cartesian problems that have nice cubic boundary conditions, or boundary conditions on a cube if you're in 3 dimensions, like the 3-dimensional square well, or the 3-dimensional harmonic oscillator is a good example of that. But if you solve a problem that's got spherical symmetry, you always use spherical coordinates, and you end up using these operators. But notice these are differential operators, so you can say right away that the wave functions are going to be wave functions in spherical coordinates, right? And over here, the wave functions would be in Cartesian coordinates, right? And notice that I don't have time as part of these wave functions, right? But wave functions have a time dependence, right? There really should be a time variable in there. For example, let me see if I can add my little t, right? I want to add time here. The way you handle time dependence in the elementary quantum mechanics is through the time-dependent Schrodinger equation. However, in almost every circumstance, we're going to deal with the time-independent Schrodinger equation. And then we add time evolution, dynamic evolution, to the eigenvalue, eigenfunctions of the energy operator. We'll talk about that a little more in a moment. But the point is we're looking for wave functions that are only functions of position, and then there's some other function of time that we have to multiply by to get the true total wave function. All right? So we'll But so right now we just can, the point of that is we're considering our wave functions only as functions of position. So we end up with these differential operators. So we've gone through this, we've taken our classical notion of angular momentum, done our canonical quantization, and developed these differential operators that now are the differential operators just as legitimate as P and just as legitimate as X. They are now the operators for angular momentum. So we look at these things and we think of them in terms of the context of the postulates of quantum mechanics. What are the big questions? Is this Hermitian? Because if it is Hermitian, we know that it's an observable. And then we know that it has eigenfunctions. And we know those eigenfunctions will have real eigenvalues. And we also know that the state of all possible wave functions that are consistent with these operators is spanned by the eigenfunctions of a complete set of commuting observables that if we can muster them up, right? And in this case, the complete set of commuting observables for most of the problems that we look at in elementary quantum mechanics that deal with this topic is the energy operator, the Hamiltonian, the total angular momentum, and the component of the angular momentum in the z direction. These three form a complete set of commuting observables. So that means they share eigenfunctions, and the eigenfunctions that they share cover the space of all solutions to the Schrodinger equation defined by the problem, right? So once we have these operators, now we can create any operator that is built out of these guys, which includes L squared, and that has its own differential form. Notice it's a second order differential operator, right? And we can create even these raising and lowering operators, and they're very important too, but they're not Hermitian, right? You got this e to the I phi part in here, right? And these guys are a sum of two Hermitian operators, but it's a complexified sum, right? It's Lx plus I Ly. And that messes up the hermiticity. And you can kind of see, if you look at this sine phi and this cosine phi, these pieces are going to come together. And when they do come together, you're going to end up with, through the Euler expression, you're going to end up with this thing. And then you got this beautiful cotangent. I don't understand why they don't go with cosecant and forget the fraction, but typically they leave it with sine squared in the denominator. They're happy to use cotangent here, but not cosecant there. Anyway, but these are still differential operators, and they're still looking for functions of spherical coordinate position. So you go from there, you can go to there. Now, once you've wandered down to this part, now you go back to the postulates, and you have two possible paths through the postulates. You can just say, well, look, I know that I have complete set of commuting observables. I can actually check that this L squared commutes with all of these, and I can check that LZ commutes with these other things, or I can check that LZ commutes with L squared, rather. And as long as the Hamiltonian is only dependent on the radius, right, which means as long as the Hamiltonian is spherically symmetric, meaning the Hamiltonian of the problem is a function of R only. So, for example, 1 over R dependence of a potential, for example, would be a good example of that. Or a square well that just changes abruptly in potential at a certain value of R. As long as the Hamiltonian is only a function of R, then I know that the Hamiltonian will commute with L squared and it will commute with LZ. And that would be my complete set of commuting observables. So once I've gone through that process and I said, well, I want to find these eigenfunctions. I want to study what are the eigenfunctions of L squared, what are the eigenfunctions of LZ, and I know those eigenfunctions will be part of our total solution. So I can just go ahead and write down these eigenvalue equations, right? Now, here I've kind of gone a little far with it, but the basic eigenvalue equation you're going to solve is something like this. L squared, this differential operator, right? That's this complex differential expression. It just gets complex. I shouldn't say complex because it's actually not. It's not, this is complex, right? This is not complex. This differential expression put right, acting on psi is some constant times psi, and that is a differential equation that can be solved. And when we solve that differential equation, we end up with this value of psi, which is a real no-kidding function, which we'll talk about in a second. And we also learn what the eigenvalue is. The eigenvalue is this h bar squared L plus 1, right? So that's really cool. And we can do the same thing for LZ. We can actually find out what this eigenfunction is for LZ. In fact, I probably should, since they commute, they need to share the same eigenfunctions, which is the way I've written it down here. You learn that they actually share the same eigenfunctions. So the process then goes from here to here, like this, right? You're now working on finding the eigenvalues and eigenfunctions directly from the eigenvalue equation, this guy right here, which I'm going to erase because it's not part of the mind map. And when you do this process, when you do this solution and you actually find these values, and we're going to discover in a moment, I've got the actual values over here. The answers are these spherical harmonics, right? And when you have these mutual eigenfunctions, you learn that the only way they work is if L is an integer. And M also has to be an integer, and it has to be, the absolute value of M has to be less than or equal to L. That is discovered directly from the analysis of these differential equations and is a direct result of these particular differential operators that come directly from our canonical quantization process. So the canonical quantization process goes through the Cartesian operators, which quickly can be converted unambiguously to spherical form, which provides you all of these operators, these differential operators, which allows you to create differential equations, and the solution of those differential equations force these eigenvalues. I guess the way to say it is there's many different solutions. Yeah, this should be a little bit more careful. What you discover is that phi, for example, is labeled. There's an infinite number of these guys, and it's labeled with a quantum number L, right? It's still a function of theta and phi, but there are different, there's many solutions depending on your choice of the value L. And once you've chosen L, the eigenvalue is L times L plus 1, right? And the same is true here. The same is true for LZ, right? It turns out LZ has L and M because they share, right? They share eigenfunctions. So you would write L and M, the LM version of the solution, right? And likewise, once you've done them both, you can then realize, oh, heck, these are both the same, so we're just going to give them the same labels, right? And so these now become the eigenfunctions, and they're labeled with two quantum numbers, L and M, and those quantum numbers are restricted to integer values for L, integer values for M, where M must always be, the magnitude of M must always be less than L, and that's forced upon you by the analysis of the differential equation, right? And ultimately, the bottom line solution is these guys here, right? These guys here are literally given by the spherical harmonics, right? So you end up at the spherical harmonics through this analysis of these eigenvalue equations. So the point of this route through the mind map is you start with the classical commutation relations, the classical angular momentum, do a canonical quantization, get a bunch of differential operators, solve the eigenvalue equations directly, and you end up with the spherical harmonics as the answer for psi LM. And we'll talk about the spherical harmonics a little more from the other angle once I want to get there a second way. So the other possible path through this is you follow the same path through the creation of these differential operators. But instead of going to the eigenvalue expressions right away, instead of saying, okay, these differential operators are Hermitian, so therefore they're observables, therefore they have eigenvalues. Let's find those eigenvalues and eigenfunctions and get that under our belt. You say, well, I've got these operators. Let's just solve problems, right? Let's just instead go right to the Schrodinger equation, right? So we go this way. And let's write down some Schrodinger equations and solve them using our new operators. And so you come up with a Schrodinger equation. This is supposed to mean that this r here is the wave function. Well, this phi, capital Phi, is the wave function. R is supposed to mean some position coordinate, right? So r is a stand-in for r theta phi, right? This is in spherical coordinates. We're going to solve the Schrodinger wave equation in a spherically symmetric system. H is not a function of time, but H is a function of r only, right? So H is only a function of the radial coordinate. See, I guess I used r in a weird way here, right? If I was a little bit more disciplined, what would I have done? I would have written it this way. I would have gone, let's see, how would I have done it? I would have said, first of all, H is only a function of the radial coordinate. Phi, the wave function, is a function of, let's see, hold on. The phi is a function of r, theta, and phi, right? R, theta, and phi. See, that's a little clearer, right? And so let's just solve some problems like that. And then we pick a problem and we write down the Hamiltonian, and then we solve that differential equation. One good example of this would be the free particle. The free particle where this gradient operator is written in spherical coordinates, right? A perfect example. And we know that the solution, the wave function solution, will have some energy. What I probably should have done is, in this case, what I probably should have done is EK is, because if I have E sub k, it evokes k as being some kind of integer. I should probably just put k right there as the energy value, because this is likely to have an infinite number of solutions, right? This is going to be a continuous set of momenta k that will satisfy the free particle Schrodinger equation in spherical coordinates. But another example is not the free particle. Here I replaced this gradient squared operator with its alternative symbol, triangle, just for variety's sake. But here we have some potential minus the energy of the particle. So let's see. Let's do this. I might do that as k, just to, again, eliminate the idea that, it could very well be that, these sorts of problems have continuous spectra and discrete spectra both, if it's a finite square well, for example, even in spherical coordinates. The point is, though, that V can only be a function of the radial coordinates, right? Otherwise, you lose spherical symmetry, right? The definition of spherical symmetry is that every relevant thing in the problem depends only on the radius. And so we can now take this Schrodinger wave equation and we can write it in spherical coordinates, and that's what you get right here, where what I wrote down as V up here, is actually U. And notice they've explicitly said U is a function of R. Psi is the wave function. E is some continuous or discrete energy. And then you see it's got this radial piece and it's got this angular piece, although the angular piece, if you look carefully, still has a radial part in it the way it's written here. But you can definitely pull that radial part out, and what's left behind, this 1 over sine theta, d phi theta, sine theta, d phi d theta, and 1 over sine squared theta, d phi d psi d phi squared, or the second derivative of the wave function with respect to the azimuthal variable. That part will end up being the total angular momentum. And it has this leading factor that does have an r in it, but that's not a big deal. You can multiply through by r and execute the process of separation of variables. So what happens now is we're now going to take our Schrodinger wave equation, write it out explicitly in spherical coordinates, and then solve it. And when we solve it, one of the things that's going to drop out are the angular parts of this is going to be the spherical harmonics. So what's going to happen when you do this, and what should be somewhat familiar to you, I would hope, is that you learn that psi is a function of r, theta, and phi. Right? That function is actually a radial function of r only times a function of theta only times a function of phi only, right? This is called the separated form of the wave function. And that leads to this process called separation of variables. And what we ultimately learn is that this piece, the product of these two parts, that is given by these spherical harmonics. And so we end up at the spherical harmonics regardless of what you choose, what problem you choose, as long as it's spherically symmetric. As long as it's spherically symmetric, you're going to end up at these spherical harmonics, which is exactly the same place you would have ended up if you had just determined the eigenvalues using the postulates of the eigenvalues and the eigenfunctions. You end up at the spherical harmonics. Using the Schrodinger wave equation and just solving some problems, you end up at the spherical harmonics. Now, if you come down this route, you also end up having to solve for this thing as well, right? Which is a totally different differential equation and is really, really interesting. The problems you usually use to get here are the free particle, in which case this guy, I think, is the associated spherical Bessel functions, right? Well, not associated, just the spherical Bessel functions is the solution when this is a free particle, when u is basically 0. On the other hand, if you're dealing with the hydrogen atoms, these become the Laguerre polynomials. And if you're solving, say, a finite square well, then these guys become, well, they're different. I forget exactly what it was. There's some bound states, and then there's some free states in the, well, there's bound states and free states in all of these, really. But the point being that you have, if you come down this route, you end up with a radial equation too, and that does not show up if you go this way, right? If you go this way, you're just learning all about the angular eigenfunctions, and then later on you have to apply that to solving this route. Inevitably, you've got to go both ways, because someday you've got to solve a problem, and the only way to solve a problem is to solve the Schrodinger wave equation. I'm just showing you different ways to get to the spherical harmonics, and you kind of got to land here at the spherical harmonics. It's the properties of the associated Legendre functions that tells you, that restricts these values to just L, right? And these values of m to being an integer, and this value of L to just being an integer, and m to just being an integer less than or equal to L, the magnitude being less than or equal to L. And so you've got to get here to figure that out. And also, if you want to just know where your electron is in these various problems, like the hydrogen atom, if you want to know where it's likely the electron is, and you know the energy of the electron and the angular momentum of the electron, and the angular momentum projection, say, that is, you know that it's in an eigenstate of these guys, of L squared or Lz, this function tells you where that electron spends its time. It's most likely to be found. From an angular perspective, right? It'll tell you what, relative to the z-axis, where is this electron most likely to be? And then, of course, to figure out where it's likely to most be as a distance from the atom, you would need this guy, right? So you got to solve all this stuff. But the point is, you got to end up here to really not only solve your problems, but also to interpret these complicated differential equations, because they're both, all these differential equations are actually ends up, for the angular part, end up being the same. The angular differential equations, when you separate this as long as it follows the rule that the potential is spherically symmetric, the differential equations you solve to going this way and this way are the same for the angular part. This way doesn't even have a radial differential equation. This way, of course, does. Okay, so you kind of got to get here. And when you do get here, that's when you learn about the restrictions on on L. Is purely through the mathematics of these special functions, the associated Legendre polynomial in particular. Okay, so that takes care of the most common path through this subject. It's a very important path because I think it's elementary E&M where you first learn about separation of variables, like when you study the waveguide. But the quantum mechanics is where you really push separation of variables out and you really start exploring all kinds of problems that uses separation of variables. And so you've just got to face what these special functions are. You've got to learn about all of these exotic differential equations that have cataloged solutions, and this is among them. And you got to kind of learn to use these catalogs and get comfortable with them. And in each case, I do feel like you need to solve them yourself to really own what they mean. So this is like the legwork of quantum mechanics at an introductory level, is to go through this canonical quantization, differential operators, solving for wave functions. Okay, so there is, however, a slightly alternative path for the introductory course, and let's talk about that in a moment. Well, actually, I think what I'll do is we'll do the next lecture on the other path. But the other path starts wandering very quickly into this abstract formulation. It kind of starts at the classical thing, just like before. That's what makes it elementary, right? Is we're starting with this classical piece, but then we move over into this abstract analysis, and that leans on our Dirac formalism as opposed to the wave function formalism. And what we'll do is we'll cover that in the next lecture. Okay, see you next time.